One powerful analytical and design technique is called voltage division, and it has a wide range of applications when analyzing circuits or designing circuits. So let's take a look at this circuit where it consists of a series connection where we have a voltage source as an input to 3 resistors. We can use KVL, and we'll start at this point right here, work our way around where we have minus Vs, a voltage rise, and a voltage drop of V1, V2, and V3. So writing this KVL equation, voltage rise is Vs, which is equal to the sum of the voltage drop across resistor R1, across resistor R2, and the voltage drop across resistor R3. Now, since these are resistors, we can use Ohm's law, and we note that since they're connected in series, this current I goes through R1, R2, and R3. So that's just simply equal to I R1 plus I R2 plus I R3. We can factor out the I, so we have I equals R1 plus R2 plus R3. Now the voltage division is used when we want to find the voltages across various elements here. So we note here that V1 is just simply I R1. Now if you note this equation here, V1, and this one with Vs, we can just simply use these two equations and get a relationship shown as follows. V1 divided by Vs is equal to I R1 divided by the sum I times R1 plus R2 plus R3, which I was going to say earlier, the sum of these resistances. Well, we note that the I's cancel here and here, and so that yields R1 over R1 plus R2 plus R3. We can solve for V1. We just simply multiply Vs on both sides, and now we have Vs times R1 all over the sum of those resistance, R1 plus R2 plus R3. Note we can use the same relationship to get the voltage across V2, which is equal to I R2. And when we do that, we'll get a similar pattern of V2 is equal to Vs divided by R2 all over the sum, R1 plus, let me clean this up, plus R2 plus R3. And then we can finally get V3 if you follow the same pattern where we just divide V3 over Vs, and we note that V3 is equal to I times R3. And when you do this, what we did similarly with V1, we get a similar pattern of Vs divided by R3 over the sum of R1 plus R2 plus R3. So if you note this pattern, you can see that the series connection, the voltage across each resistor is equal to its resistance divided by the equivalent series resistance of the connection times the voltage across the series circuit. So in other words, we see that the voltage divider divides among the series resistors in proportion to the resistance over the equivalent resistance of the series connection. So here's our relationship associated with V1, V2, and V3, and we note the pattern is just simply the ratio of whatever the resistance it is that we want to find the voltage at, divided by the total resistance that is connected in series. Now we'll go through some examples. Okay, let's apply this voltage division technique with this example where we have a 24 volt connected to 4 series resistors, 100 ohms, 560, 330, and 220. So let's find the voltage of VO, then we'll find the voltage across VX and VY. So the voltage across VO corresponds to the 330 ohm resistor. So VO is simply 24 volts times the 330 ohm resistor divided by the sum of all the resistors that are in series. So this is 100 plus 560 plus 330 plus 220, which is just equal to 24 divided by 330 over 1210, which is just equal to 6.55 volts. So that's our answer associated with the voltage across VO, which corresponds to the 330 ohm resistor. Now let's calculate VX. We'll follow the same process, 24 volts, and that VX is associated with the 560 ohm resistor, and we just divide that by 1210 ohms, which we calculated earlier, and that's equal to 11.1 volts. Then we have VY, which is 24 volts, divided by, and VY is with 220 ohms, divided by 1210, and we have 4.36 volts. So our answer for VO is 6.55 volts. VO is across the 330 ohm resistor. For the 560 ohm resistor here, we have a voltage across it of 11.1 volts. For VY, which is associated with the 220 ohm resistor, we have a voltage of 4.36 volts. So this is just one example of how to apply and analyzing a circuit using voltage division.